Hello everybody, welcome to the Henstitute. Today we're going to be talking about the Doppler Effect. If you're a Big Bang Theory fan and you watch the show, there was an episode that I put into the last one. Actually, it was someone else added it to their little video on the Doppler Effect, in which Sheldon actually dressed like the Doppler Effect, and his excellent example was commonly to tell people, listen to this. And the idea, if you were standing on the side of the road and say a motorcycle drove by, that's usually what I think of as a motorcycle, but it could be a car or a train, anything that was kind of moving by, you're going to hear a change in the frequency. So the Doppler effect itself is, so let's get Doppler, is an apparent change in frequency. And you'll find out why I say apparent change in frequency due to relative motion between the source and the source of the wave and the listener or the observer. Between source and I'll say observer. Because one of the things I thought was kind of neat about the video I sent you is they also talk about red shifting. They didn't bring up the idea of blue shifting, but light itself being a wave also exhibits these same characteristics. So that was kind of neat. So the Doppler effect was first proposed by an Austrian scientist by the name of Christian Doppler. Now, Christian Doppler in 1842 came up with this idea about light actually affecting this Doppler effect, so this apparent change in the frequency of light. He was looking at binary stars, so we kind of consider him a mathematician, but he's almost like an astronomer, and that's where it came from. And then later we got scientists that looked at it in terms of sound. It's probably most commonly affected with sound in most everyday life. So I love this picture over here to the side. So what it's got is we have some truck and it's at rest. And the idea is this truck is producing some kind of sound. So the sound is traveling out in all directions from this truck. And these are supposed to be like compressions in the wave, or they say condensations, but compressions are the same idea. So this person standing over here, this distance from here to here would be a wavelength, and they're going to hear the sound. And this person back here, they're also going to hear the sound. And they would hear the same sound. Because if they are not moving and the truck is not moving, then the sound waves just travel out in directions equally. But when you switch down here, now what we have is we have the actual truck is moving in this direction. So we have the speed of the source of the sound. So I'm going to call this Vs. And the speed of the source, what you see, I love this picture, is as they are sending out the sound waves, every time they send out a sound wave, that sound wave, they're moving toward it. So what ends up happening is they get bunched together. So all these sound waves are getting bunched together. And so this person over here on the right is actually going to experience a smaller wavelength. Now, why is this important, and why do we say an apparent change in frequency? Because if you have a smaller wavelength, we know that the speed of any wave is equal to wavelength times frequency. So if our wavelength gets smaller, our frequency would actually have to get higher so that this stays the same. Because this would actually be the speed of sound. So this is going to be the speed of sound. And the speed of sound is not going to actually change. It's going to stay a constant as long as we're dealing with the same stuff here. So if our wavelength gets smaller, our frequency has to get higher. And when we refer to frequency that are higher, we refer to this as the pitch of the sound. So it's going to get a higher pitch, and therefore you're going to hear that higher frequency. So we refer to the frequency, and we always refer to it as an apparent change because the frequency is not actually changing, but it appears that way. On the opposite side for this person is, you notice we have a larger wavelength happening, and therefore we're actually going to get a smaller frequency, or a lower frequency is usually what we say. So I'll say lower here. And that's what we actually kind of experience, that lower pitch. So how do you actually calculate the Doppler effect? So I erased all of our stuff for the Doppler effect here because I want to get our equation. How do we actually go about it? Now, one of the things is, if you notice, I have the source actually moving, but when we mentioned the Doppler effect, we actually mentioned it was a relative motion. So you can also have the observer, so you could have the observer actually have some motion as well. This person could be moving toward the truck, and that would cause this higher thing, or if this person was moving away from the truck, this would actually cause our larger wavelength. So our general equation is going to look fairly ugly, but I want to make sure that we've got all the parts to it. So the first part of it is our frequency that we actually observe. So I'm going to put FO on here to stand for frequency you observe. It would equal the frequency of the source. So that's what the S stands for. So this is our observation, observe, and this is going to be source. Now, the next part of this is those two would equal each other if nobody was moving. That's basically our situation up here. But if they are moving, then we have this extra fraction that we have to take into account. So I'm going to write the parts of the fraction. So it starts off with a 1 in front, and then I have a plus or minus on the top. And this is going to be the speed of the observer over, this is actually the speed of the wave. So I'm going to put a little W on here to say wave. In the equation you're going to see a little bit later from the book, they don't actually have anything on here for the V, they just have V, but I just want to remind you that this is the speed of the wave. So this top part, if the observer is moving, if they're moving toward the truck, you're actually going to get a higher wavelength. So you would actually have the plus on this, so that this would be a larger number. This would be larger than 1, and therefore the observer would be a higher frequency than the source. If they're moving away from the truck, that's going to actually be negative, and therefore you'd have 1 minus this little fraction. And if I have 1 minus this fraction, this is going to be less than 1, and therefore I would actually observe something that is a smaller or lower frequency. On the bottom, you're going to actually see me write this the other way. So I'm going to put a minus, and I'm going to put a plus, and then I'm going to put Vs, that's going to be the speed of our source, and then again, we just have it over V, but just for right now, I'm going to write the word wave here so you understand it's the speed of the wave. This one's a little bit different because if the source is moving toward our observer, what we actually want is we want the bottom of this to actually be a smaller number than 1. So the way we do that is we put the minus on top if they're moving toward each other, and then if they're moving away from each other, we put the plus. So you always do whatever is on top. So the top is when you're moving toward, and the bottom is away. Now, when I say that, this top and bottom part, I'm actually talking about the plus or minus here. So I'm talking about this section or this section. So if I'm talking about addition or subtraction. So you have to kind of take that into account when you're actually using the Doppler effect. Is the object moving toward the observer or the source, or moving away? Is the source moving toward or away? And so the top is always, the top one is if things are moving toward. So if the observer is moving toward, you would use plus on the numerator here. If the source was moving toward, you would actually use minus for this particular fraction. So you'd subtract it. So it's kind of weird. We can't always say that toward means positive and away means negative, because we have to kind of change out our equation a little bit here. So this is the Doppler effect. We're going to play around with this lovely little equation and see what we can kind of figure out. I hope you enjoyed this edition of the Henstitute, and I will talk more with you later this week.